last presentation of the day, also to kind of sum up a lot of the themes that we're running through the course of the presentations, and also to kick off a discussion for us about how we're going to develop our work in ZeroPM further when it comes to substance grouping. So just going back maybe to earlier, before we talk about substance groups, I'm going to break up my talk into address using the deep data approaches that we discussed today for addressing data gaps that was presented earlier, but also how we can prioritize PM substance groups as an act of co-creation. And right now we have a perfect venue for such co-creation. Now, in terms of prioritizing PM substances for addressing gaps, this is what a lot of us were presenting this morning. We can look at all the chemicals that we're producing on the global chemical inventory. We can have probabilities about them being persistent and mobile and their likelihood of transformation products. And this is a good way for starting to address gaps related to these. And this figure here, this is from a 2016 paper that was predating ZeroPM. It's from a project called JPI Promote, which kickstarted a lot of the conversation, I think, about persistence in mobile substances. And there we're also looking at other gaps in addition to substance properties. And these were also, at the time, the substantial analytical gap and the regulatory gap. So at that earlier project in 2016, we looked at the substances that were currently being regulated. And one thing to notice was that a lot of them were not so mobile. So if you look at the DOW, which is the optimal water distribution coefficient, as a proxy for mobility, a lot of the chemicals that were being regulated were not that mobile, not that water soluble. But we could also link that to an analytical data gap, because at that time, we didn't have, like even 10 years ago, we didn't have the same analytical capacity in liquid chromatography that we have now. So data was being generated with RPLC or polar modified RPLC to get, or GCMS, so there's a lot of data on how to get the not so mobile compounds with a high DOW value. But since then, there's been a lot of research into more mobile methods, such as hydrophilic interaction liquid chromatography, ion chromatography, capillary electrophoresis, and supercritical fluid chromatography. Not all of the methods can get all of this mobile chemical space, but they can get some. But we also saw this was important, as was brought in the presentation this morning by Eric Schmolz, that a lot of these compounds were falling in an analytical and monitoring data gap. This is one of the initial reasons for looking at persistent mobile substances. And in that report that was introduced this morning, we did do an interview of all the analytical labs around Germany, and we gave them a list of 150 potentially PMT or known PMT vPvM substances, and asked them, could you measure this? And there's still a handful of substances that all labs say they had an analytical gap. They would not know how to analyze this, even if you gave them a lot of resources. And there was 21 substances that thought, we don't have in our lab a method to analyze this, but maybe we could develop one. But even if they did have the methods, maybe they had a supercritical fluid chromatography apparatus, they're not monitoring for that because nobody was asking them to. And so these were chemicals we prioritized and asked them, could you measure that? And nobody says, well, we could, but nobody's ever paid us money to it. So there's still a lot of analytical and monitoring gaps out there. And there's also mentioned remediation gaps, because a lot of these substances that are persistent and mobile in the environment are also persistent and mobile during drinking water production. If they have a log KOC below 2, that's also used as a proxy to say if activated carbon or granular activated carbon is an okay remediation approach using a standard GAC bed. So very mobile substances tend to be permeable to these GAC absorption filters. And a lot of the compounds that couldn't be reacted with ozone because they didn't have a double bond to cause that reaction. So it could also prioritize chemicals based on their ability to be removed. And this is here when we ask there's 13 different water remediation facilities. These were the substances that they were having the most trouble with TFA, 1,4-dioxane, EDTA, nolamine, benzoyl, triazole. So these were chemicals that they were prioritizing for the protection of their consumers of their drinking water. So this was part of that initial prioritization framework that we developed earlier that was presented this morning, looking at also, first, of course, the hazard of PMT or vPvM, but also what's the likelihood of emissions, is there an analytical or monitoring data gap, is there a remediation gap, and what's the current exposure level. But now we are trying to look, this is more about how we prioritize individual substances, and what we're doing in ZeroPM is trying to prioritize substance groups. And this, I think, requires not just us coming from, say, the chemistry side, the research side, the cheminformatics side, the data science side, but we need to know what you, from the different stakeholders you have in the audience, the water treatment facilities, the chemical industry, the regulators, what do you want to have from this data? We have an interlinked strategy in ZeroPM. We are particularly prioritizing PM substance groups based on intrinsic properties, exposure, and hazard to select those substances to prevent, such as by stopping to produce them, by finding alternatives, or to remove by developing new removal technologies most urgently. And we do this through the stakeholder approach of our multi-level framework. So, now we're going to be looking for PM substance groups going forward on the global chemical inventory. This is one of the next tasks in ZeroPM. I showed earlier that we're also using existing definitions of grouping that can be found in REACH to make it REACH compliant. So it has to have a common functional group. It has to have a common precursor and or the likelihood of a common breakdown product via physical and biological processes, which result in structurally similar chemicals, or a constant pattern in the changing potency of properties across the category. Well, so we're showing now, one of our first grouping methods, as Parvil just presented, is based on a common functional group. And as he also presented, we have the second approach of looking for dead-end transformation products of various precursors. Now, what we're going to do now, and also develop in our discussion cafe, is looking for us, what are we prioritizing when we're looking at these groups. So within ZeroPM, we also have these discussions. With our work package 2 and alternative assessments, we talk about opportunities to find alternatives, what type of approaches we can make to find alternatives, especially if it's persistent mobile substances. Maybe there's already existing alternatives on the market that could help us look at that substance group. We're also looking at policy gaps and opportunities. Where are there opportunities to make a regulation for a particular group? This is part of the work of work package 3. In work package 4 with ChemSec, we're looking at what is the potential for a market transition. How can we talk to chemical manufacturers? What are the substances that they would like to introduce to the market as the greener alternatives to these potentially problematic persistent mobile substances? We are looking also for prioritization through a risk assessment framework. This will be presented tomorrow. And of course, monitoring and remediation to address the remediation gap. But this is all about working together to identify these substance groups. So these are different steps. So we can start with our 3 groups, the small PFAS, the trizones, and the trizoles. And we can look at ways that we're looking at them in work package 4, or work package 5. We can look at the exposure data. So what are the additional levels of data that we can put on these groups? We can look at production volumes and emissions if we have it. We talked about uses a lot. So what are these chemicals used for is important information that we need to know. Monitoring data is important in transformation reactions. There's also several hazard categories that we have to look into. Human toxicological hazards, which is a big focus in ZeroPM. But of course, there's also ecotoxicological hazards. And for the vPvM category, different geophysical and aesthetic impacts that we have to be mindful of, such as, is this chemical an odorant? Does it make the water sweeter? Does it affect the taste? Is it a UV visible light filter that can, for instance, darken river water bottles? Is it a surfactant, or that would affect water properties in the environment? Or is it ozone depletion? So there are other geophysical impacts that we also keep in mind. But ultimately, for prevention, we want to know these things for a large set of data and for substance groups to avoid regrettable substitution and also to avoid regrettable remediation. So I'm just going to give some examples. And one of the things that we've talked about a lot in ZeroPM, and this was just brought up by one of the previous questions of Emma Shemanski's talk, and that was, what about uses? Can uses help us focus? And I think there's a lot of ways we can talk about that in the ZeroPM framework, because if we have a problematic PM substance group, we can consider our work packages. And if we have the uses for this group of substances, we can look at ways of finding alternatives for that group. We can look at development policies. If they're being used as biocides, we can look at the biocides policy. If they're being used in the pesticides, we can look at the pesticides policy. If we're looking in REACH, we can look at REACH chemicals, we can look at REACH. Also the market potential. This will also help for uses that will also give us a big clue for exposure pathways. So for instance, risk assessment is more closely brought into the biocide regulations, into the pesticide regulations, particularly because they know what the chemical is used for. That helps with REACH chemicals, as Mike Grassenberg said, you don't necessarily know where that chemical is being used, what it's being emitted for. And then also to put them in non-target approaches, then we can also look at suspect screening, monitoring campaigns, seeing if our drinking water treatment is sufficient. So just to give you some examples of uses that we are being discussed, a big topic now going forward in work package 2, Ian's work package, is the small PFAS used in lithium-ion batteries. Do we need PFAS in batteries? That's a question that we can ask further. We know that there is exposure. We're measuring these chemicals in drinking water now. They're very persistent and very mobile. Their toxicological hazards are currently known, as far as I know. But there's also alternatives to lithium batteries, and there's also these other interesting chemicals that are alternatives, which we know almost nothing about, which are likely very persistent and very mobile. Daniel Zahn was here. I remember at CTEC, right there. He was measuring extremely high concentrations of these two chemicals in drinking water. They're alternatives to these ones, so this is a very right thing to discuss. We can also go back into looking at fluorotolerable sulfonates, typically used in aqueous film forming foams. So the fluorotolerable sulfonates are one of the most frequently used replacements for PFAS and fluorohexosulfonic acid in these foams. And now we're seeing them more in the environment, and also some of the work done by, in work package 6 by Timur Bagdiev, who's not here. He was finding his starting some, has some TTR binding potential from effect-directed analysis in monitoring studies. But it's not really yet classified as being a toxic compound. It's vPvM, but we should look at that in more detail. And of course, prevention, there is alternatives to PFAS-containing AMPFS. And it's also, we can look at removal strategies, because what we don't want to do is go to smaller FTSs, because these will be, as we know, harder to remove. Another example that I like to discuss a lot are these guanidines that we see used in car tire agents. There's not much regulatory action on them yet, but we find them in extremely high concentrations, particularly after rain events. So anytime there's a rainstorm in an urban environment, and there's methods now that I've seen to monitor these in real time, we'll see huge spikes of these persistent mobile substances entering water resources. If you're sampling after a rainstorm, you might not see it because they're so mobile they already got distributed. I don't know about if there's alternative to these, but one thing that is, they're not so hard to remove if they're treated by ozonolysis. We can also look at the continued use of chlorinated organophosphate flame retardants. These tend to be more persistent than their non-chlorinated counterparts. They're kind of on the border of being mobile or not, but these are chemicals that we know that they're there could be alternatives, chlorinated to non-chlorinated, for the removal of drinking water after a bit of carbon is required. But a lot of these are associated with carcinogenicity, toxic to reproduction. So there's a case to be made that chlorinated organophosphate flame retardants could be substituted for less persistent and mobile alternative flame retardants. But that would have to be looked. And we also looked a little bit at benzophenols, these are UV blockers. One of the early studies from Work Package 2, they're talking about benzophenols used in cosmetics. And we can already find safer UV filters to benzophenols. So this was the work of Ume and Figuera, who's here. But we can look at the persistence and mobility first of the different benzophenols on the market, see which is the safest, but also look at alternatives for these. And finally, there's what I consider the OG of persistent mobile substances, the original generation. These were actually the chlorinated solvents, like these dry solving cleaning agents. These were regulated before, these were issued to drinking water before PFAS. They're still a major issue. A lot of countries are still struggling with high amounts of chlorinated solvents in their groundwater, and these are still being produced and used today, but we don't really know what they're being used for, other replacements. And another interesting one is also di-associated aminobenzenes and diamines. So these are just some structures that are associated. This is kind of a new category for us to look at these kind of di-associated compounds, but we can say from earlier work in Work Package 2 that when you're having a dye, you have to look, is this a dye that's used for marketing purposes, or is it actually used in the product? So this goes into essential use. If it's just being used as for marketing purposes, you could say that's not an essential use of a dye. If it's of course being used to give a lipstick a particular shade of red, and that's useful. But then once you get there, once you know what it's being used for, is there a safer alternative to get that exact same pigment? So this is something we could approach with these dye-associated, persistent and mobile diamines and aminobenzenes. Yes, and then finally the trifluoroacetic acid precursors. This is also a big topic for us because TFA is a substance that's accumulating in the environment, and currently the hypothesis is that it's refrigerants that are mainly responsible, and that is most likely true in several areas like the Arctic. But when we see some of the TFA concentrations that we're seeing in groundwater and water resources, we know that there's a lot of other sources currently unknown. So a design question is, can we make alternatives to these TFA precursors? And this can be in pharmaceuticals, it could be in plant protection products, or other chemicals that contain TFA as a transformation product. And there's a poster out there, you can see it in more detail, but this is just a graph showing that TFA has been increasing exponentially in pretty much any environmental media you can measure, including in every plant, in every animal, and every human. So, this is all I'll just conclude for now, and this will all lead us up to the discussion cafe. That grouping PM substances based on specific molecular substructures will support PMT vPvM substance prioritization and directed risk assessment procedures. Grouping can be done by common moieties amongst PMT vPvM substances and dead-end transformation products. For prioritization, going forward, a big thing for us will be use creators, but also an important thing, and this is what we want to talk with you soon, is co-creation amongst scientists and stakeholders to find those that we need to prevent or remove most urgently, such as by risk assessment, and this will be the talking about tomorrow with Work Package 6. So with that, I want to thank you very much for your attention.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.